Yeah, good evening again. In today's lecture of mole and stoichiometry, we are going to do concentration terms, including molarity, molality, mole fractions, and all these things. So till now, in previous lecture of mole concept, we have done basic mole calculations, and apart from basic mole calculations, the calculations related to chemical reactions known as stoichiometry. So in today's lecture, we'll do concentration term including molarity, molality, percentage Y weight, percentage Y mass, percentage Y volume, and we'll see their interrelation between molarity and molality also. So let us start today's lecture. First, we'll define different concentration terms. So first thing is, first concentration term, it may be, let's say, concentration by weight, or you can say it is concentration by percentage. Concentration by percentage. So concentration by percentage. So concentration by percentage, and its A part may be, let's say, percentage by weight. Percentage by weight, or it may be written as W by W or percentage by W. Let's say. So it is percentage W by W. It is percentage by weight. So it is mass of solute in 100 gram of solution. It is mass of solute present in 100 gram of solution. Similarly, it may be, let's say, percentage Y volume, and percentage Y volume means, let's say, percentage V by V. It may be, so it is, volume of solute in 100 milliliter of solution. And similarly, it may be percentage by weight in volume, or you can simply say it is percentage W by V. So it is mass of solute, usually given in grams, in 100 milliliter of solution. So as per concentration by percentage is concerned, so percent means obviously it is out of 100. So it is out of 100 gram of solution. It may be, let's say, out of 100 milliliter of volume, or it is, let's say, mass of solute out of 100 milliliter of solution. And if nothing is mentioned, regarding a type of percentage, it is always, percentage weight by weight. I hope you note down these definitions, including percentage by weight, percentage by volume. It may be percentage weight by volume. Next one, for example, if you can simply say 40 gram of H2SO4, 40 gram of H2SO4 in which, let's say, density of H2SO4 is suppose 1.5 gram per milliliter. So it is 40 gram of H2SO4 in which density is given as 1.5 gram per milliliter is dissolved in you can simply say this may be 800 milliliter of water, and obviously density of water is nothing but 1 gram per milliliter. So if 40 gram of H2SO4 dissolve in, let's say, 800 milliliter of water, density of water we know it is nothing but approximately 1 gram per milliliter. Then if you see percentage weight by weight, if you see, let's say, percentage weight by weight should be equal to mass of solute, which is given as, let's say, 40 gram of H2SO4. Total mass of solution become 800 plus 40 multiplied by 100. So this will be the mass of solute out of 100 gram of total solution. Same, you can say it is percentage volume by volume. Percentage by volume should be, it is nothing but 40 divided by 1.5. This is the milliliter of H2SO4 divided by 800 milliliter is just a solvent volume plus practically you can say solute volume multiplied by 100. It will be nothing but percentage volume by volume, and similarly percentage weight by volume should be equal to, it is 40 divided by total volume is 800 plus 40 divided by 1.5 into 100. It is percentage weight by volume. So one is percentage by weight, one is percentage by volume, another may be percentage weight by volume. And for example, if it is written as 30% weight by weight, yeah, if nothing is mentioned related to weight, if it is just a 30% H2SO4 aqueous solution, it always means it always, if nothing is mentioned with percentage, it is always, you can say, 30% weight by weight. So it is the mass of solute out of 100 gram of solution. I hope, is it clear? Percent means it is just out of 100. So next concentration term, this may be, let's say, mole fraction. A typical symbol of mole fraction is, let's say, the symbol as xi. So just read this as xi in Greek or Latin. The meaning of, let's say, mole fraction, it is number of moles. It is number of moles of solute out of total moles of solution. It is number of moles of solute out of total moles of solution. For example, if it is, 20%, or simply you can say if let's say you can imagine any aqueous solution which has, let's say, 400 gram of water. 400 gram of water is mixed with 30 gram of urea as solute and water as a solvent, obviously. Then the moles of water is nothing but 400 divided by 18, and in the case of moles of urea, it is 30 divided by 60. So as per mole fraction of urea is concerned, it is moles of urea, which is 30 out of 60 divided by total number of moles, which is 30 out of 60, and it is 400 divided by 80. And similarly, let's say mole fraction of water should be equal to 400 divided by 18 whole divided by 30 by 60 plus 400 by 18. So mole fraction of urea and mole fraction of water. So fraction, it is fraction means out of total moles, what is the fraction of particular component, and it is always mole fraction of solute plus mole fraction of solvent should always equal to 1. Total moles of solute plus solvent. So it is a number of moles of solute out of total moles of solution. Similarly, another concentration term is molarity. Its symbol is capital M. It is moles of solute in 100 milliliter of solution. As far as molarity is concerned, it is going to be most effective concentration term. So it is moles of solute in 1000 milliliter of solution. It may also written as, let's say, moles of solute per liter of solution. So as per molarity is concerned, molarity, which is capital M, should be equal to, let's say, moles of solute divided by volume of solution. Usually it is given in milliliter, so it make multiplied by 1000 such that it may be calculated per liter per 1000 milliliter. So it's moles of solute present per liter of solution, or if it is volume given in milliliter, you have to multiply it by 1000. For example, if 49 gram of H2SO4 present in 750 milliliter of solution, then molarity capital M should be equal to, then the molarity capital M should be equal to moles of solute So it is 49 gram divided by 98. 49 is, let's say, the mass, 98 is, let's say, its molecular mass. So 49 divided by 98, it is present in 750 milliliter and multiplied by 1000. So as per moles calculation is concerned, it is mass divided by molecular mass of H2SO4, which is 98, present in 750 milliliter of solution, and this multiplied by 1000 to find out in 1 liter. Should be further equal to, let's say, half multiplied by 4/3, and let's say it comes out to be 2m/3. 2m/3, you can read it as 2/3 moles per liter, or you can read it as, let's say, 2 divided by 3 and molar. So it is moles of solute in 1000 milliliter of solution, molarity. Moles of solute divided by volume of solution in milliliter multiplied by 1000, or it is, let's say, 49 gram of H2SO4 present in 750 milliliter of solution. Effectively, molarity may be written as moles of solute out of 750 multiplied by 1000 and comes out to be 2/3 molar. Molar represented by capital M, and it may be read as molar or moles per liter. Similarly, as term molarity is concerned, we have different representation for molarity. For example, if molarity is 0.1 moles per liter, it may be written as, let's say, 1/m. It is 0.1 m or 1/m. It may be written as, let's say, m/10. Sorry, it is m/10, and you can read it as, let's say, deci molar solution. 1/10th molar. Same if it is 0.01 mole per liter, it may be written as m/100, and you can read it as centimolar solution. If it is, 1 mole per liter, it can be simply written as m, and it is molar solution. Let's say it is molar solution. Similarly, if it is half mole per liter, it is m/2, and as per solution is concerned, it is known as, let's say, semi-molar solution. So as per, let's say, different terminology is concerned, capital M means moles per liter. So m/10 means 1/10th of moles per liter. m/100 means 1/100th of moles per liter. Capital M itself is moles per liter only, and then m/2, you can represent it as half moles per liter of solution. As molarity, we know, as molarity, let's say capital M is moles of solute, per liter of solution. per liter of solution, per unit volume. So confirmly you can say moles. Moles of solute should be equal to, molarity multiplied by volume of solution in a liter. Moles of solute should be equal to molarity multiplied by volume of solution in a liter. I hope it's clear. Molarity, as it is moles per liter multiplied by volume in a liter, and it may be obviously written as molarity multiplied by volume in milliliter multiplied by 1000. Sorry, divided by 1000. So it will be volume in milliliter divided by 1000 will be volume in liter. For example, if we have to do few questions based on this, let's say question number 1 related to molarity is find out molarity of an aqueous solution. Aqueous solution means solvent is water. So find out molarity of an aqueous solution containing. Find out molarity of an aqueous solution containing, let's say 20 gram of NaOH in, containing 20 gram of NaOH in, let's say you can simply say 800 milliliter of solution. So it's easy questions. You have to find out, let's say, molarity of solution in which 20 gram of NaOH dissolve in 800 milliliter of solution. So its molarity. So it is 20 gram divided by 40 divided by 800 multiplied by 1000. So it comes out to be, let's say 5 by 8 molar. So 5 by 8 molar means it is 5 divided by 8 moles per liter. It is 5 divided by 8 moles per liter, or you can read it as a molar. Molecular mass of NaOH is 40. So mass of NaOH divided by its molecular mass divided by total volume of 800 multiplied by 1000. It comes out to be 5 by 8 as your answer. I hope it is clear how we can find out the molarity. Similarly, let's say question number 2 is find out molarity of pure water. Find out molarity of pure water at 25 degrees Celsius. Yeah, molarity of pure water without mentioning the temperature. So find out molarity of pure water. As per pure water is concerned, here you can imagine, let's say in this water, so suppose in this vessel, Suppose, let's say in this vessel, if we have pure water here, in which its amount, you can imagine, let's say this amount is given as 1 liter only. Suppose if this amount is given as 1 liter, so you have to just find out how many moles of, let's say, water present in this 1 liter of solution. So as per concentration or molarity of water is concerned, molarity of water, in 1 liter we have 1 kilogram of water as density. As density of water is nothing but 1 kg per liter. So molarity of water should be equal to, let's say it is 1000 gram. It is 1000 gram per liter. So 1000 gram means it will be nothing but 1000 divided by water molecular mass. This much moles per liter. It comes out to be 55.55 moles per liter, which may be written as 55.55 molar. So to calculate, density of any pure liquid, you have to calculate the molarity of any pure liquid. So molarity of, any pure liquid should be equal to its density which is given in grams per milliliter. Yeah, simply you can say grams per liter first, divided by its molar mass. So when it is given as, let's say, mass divided by volume, it is nothing but, let's say, grams per liter. So it is molarity of pure water. Density divided by molecular mass. It is density divided by, let's say, molecular mass in the case of pure substance. I hope it's clear now. Third question. Find out moles of solute in 200 milliliter of 0.3 molar aqueous solution of HCl. Here molarity is given and volume is given, and you have to find out the number of moles. To find out number of moles, as we have just know number of moles of solute should be equal to, let's say, molarity, which is nothing but it is moles per liter multiplied by volume of solution in liter. should be equal to, it is 0.3 multiplied by, it is 200 divided by 1000, volume in liter, and should be equal to, it is 0.0, 0.06 moles of HCl. So simply you can say number of moles of solute is molarity multiplied by volume. M into V is moles of solute. Similarly, on the same basis, let's say next question. Question number 4 is, find out resultant molarity of 0.3 molar solution if it is diluted, if it is diluted by 100%. Find out resultant molarity of 0.3 molar solution if it is diluted by 100%. So as per question is concerned, suppose initially we have some amount of, let's say any solution. So you can say it is 0.3 molar of any suitable solute, for example, HCl. So initially we have some volume here. So some volume of HCl, and the solution consists, let's say, HCl only. And its concentration is also given. As per the meaning of dilution is concerned, some water is added here. So dilution means, let's say, some water is added here. And now in this same vessel, we have volume initially as well as whatever volume we have added. So it will be total volume present basically. Initially it is HCl only. So it is HCl, and finally also it is HCl. Here its molarity is given as M1, its volume is V1. Suppose its molarity will be M2 and its volume is, suppose, let's say V2. During dilution, some water is added. Now, initially moles of solute should be M1 multiplied by V1, and finally moles of solute should be M2 multiplied by V2. Initially moles of solute and final moles of solute. During addition of water, once we add water, there will be no change in moles of solute, and thus it is M1 V1 should be equal to, let's say, M2 V2, and it is during dilution. During dilution, as we do not change moles of solute, we just add solvent. So initially moles of solute and final moles of solute will remain same. Now as per question is concerned, suppose if its volume is found to be V, the meaning of 100% dilution is we add another V volume and total volume become 2V. So if you apply the same formula here, initial molarity is 0.3, initial volume is V, final molarity is, let's say, M2, and final volume is, let's say, 2V. From here, M2 comes out to be 0.3 divided by 2 moles per liter. So let's say if initial molarity is given, which was 0.3 molar HCl, and if you have to find out, let's say, final molarity. Initially, number of moles is M1 V1, and final number of moles is, let's say, M2 V2. And you can remember this as a formula for dilution. M1 V1 should be equal to M2 V2. So next is, that's the question number 4. If 600 milliliter of water is added to 200 milliliter of 0.5 molar H2SO4 aqueous solution, then find out net molarity, resultant molarity of H2SO4. You have to find out resultant molarity of H2SO4. So as per let's answer is concerned, again it is during dilution. So you have to apply M1 V1 should be equal to M2 V2. Its initial molarity is given as 0.5 and initial volume is given as 200. Its final molarity is, let's say, M2, and its final volume is nothing but, let's say, 600 plus 200, as 600 milliliter of water is also added into given solution. This comes out to be final molarity M2 as 0.5 multiplied by 200 divided by 800, and this M2 comes out to be 0.5 divided by 4. 0.5 divided by 4 is 0.125 moles per liter, or it is 0.125 M, capital M, this much of molar. So if 600 milliliter of water is added to 200 milliliter of 0.5 molar H2SO4 aqueous solution, you have to find out the resultant molarity of H2SO4. I hope the question is clear to you. So one more question related to molarity calculation. If 200 milliliter of 0.3 molar HCl is mixed with 300 milliliter of 0.2 molar HCl solution, then find out resultant molarity. Find out resultant molarity of solution. So I'm repeating again, if 200 milliliter of 0.3 molar HCl is mixed with 300 milliliter of 0.2 molar HCl solution, you have to find out resultant molarity of solution. So as per question is concerned, here let's say we have 3 different vessels, suppose, and on mixing these two, let's say we have another vessel here. Here it is given as, let's say some HCl is present here, some HCl is present here, and obviously the total volume will present here, final volume. In this case, its molarity is, let's say, M1, its molarity is M2, and you have to find out this as a molarity. Its volume is V1, its volume is V2, and let's say this final volume is UV. So if 200 milliliter of 0.3 molar HCl is mixed with 300 milliliter of 0.2 molar HCl solution, you have to find out the resultant molarity of the solution. In this case, you can find out moles of solute present. Moles of solute should be M1 multiplied by V1. Here, moles of solute is nothing but M2 times of V2. And here in this case, moles of solute should be M1 V1 plus, M2 V2. Total moles of solute. Here we know its volume is found to be V1, its volume is found to be V2, and here total volume is nothing but V1 plus V2. So it is mass M1, volume V1, it is mass M2, volume V2. Total volume comes out to be, let's say, V1 plus V2. So final molarity after mixing. Final molarity, let's say, after mixing should be equal to M1 V1 plus M2 V2 divided by V1 plus V2. Final molarity after mixing is, let's say, M1 V1 plus M2 V2 divided by V1 plus V2, which comes out to be, let's say, 200 multiplied by 0.3 plus 300 multiplied by 0.2. As per information in the question is given, it is 200 multiplied by 0.3, 300 multiplied by 0.2 divided by 500. And I hope it comes out to be 0.24 molar. So molarity, molarity of the resultant solution. So moles of solute we can easily find out. Moles of solute in first vessel, moles of solute in second vessel, and total moles of solute in vessel 1 as well as vessel 2. Now, apart from molarity, we have another different term here. It is known as molality. Molarity represented by capital M as a symbol, and molality is represented by, let's say, small m. Molality. So it is moles of solute. As per molality is concerned, it is moles of solute present with 1 kilogram, or which is nothing but 1000 gram of solvent. It is moles of solute present with 1 kilogram or 1000 gram of solvent. So further you can say molality, which is small m, should be equal to, is it equal to moles of solute divided by, it is, let's say, mass of solvent. Obviously, again, usually the solvent mass is given in grams, so it is multiplied by 1000 for 1 kg. Moles of solute divided by mass of solvent in grams multiplied by 1000. For example, let's say if it is, it's a 60 gram of NaOH. If 60 gram of NaOH is present in 810 gram of its aqueous solution. Let's say 60 gram of NaOH is present in 810 gram of its aqueous solution. Then molality, which is small m, should be equal to, it is 60 divided by 40. 60 gram divided by its molecular mass as a 40, and it is 810 minus total mass minus 60 will be the mass of solvent only, and it has to multiplied by 1000. So as per molality is concerned, it is moles of solute, which is mass of NaOH divided by its molecular mass, which is 40, divided by mass of solvent multiplied by 1000, should be equal to, so it comes out to be 2 moles per kg. As per 2 moles per kg is concerned, it may be represented as 2 and small m. It can be represented as 2 and a small m, and you can read it as 2 molal. You can read it as 2 molal solution. So same as molarity is moles per liter represented by capital M. You can read molarity as molar. Molality is moles of solute, per kg of solvent, and it is known as molal solution. Next thing related to molality only. Let's say if molality is, 1 mole per kg, it can be simply represented by M solution, and you can read it as molal solution. Similarly, if it is, 0.1 mole per kg, you can read it as M divided by 10, and it is decimolal solution. Similarly, if it is 0.01 mole per kg, it is M divided by 100, and also known as, let's say, centimolal solution. It is also known as centimolal solution. Same if it is, 0.001 moles per kg represented by M divided by 1000, and it is known as millimolar. Millimolar solution. So as per molality is concerned, this much moles per kilogram, 0.1 moles per kg, 0.01 moles per kg, 0.001 mole per kg, molality. So the basic idea of all these concentration term is, apart from their definition, you should know how to convert them into each other. For example, if molarity is given, you should able to calculate molality. If molality is given, you should able to calculate mole fractions. Mole fraction is given, you can find out molarity, molality, and all these things. So to find out correlation between them, let's say the next question for today's lecture, I hope it is question number 6 or 7. So question number 7 is, let's say, find out. Question number 7, let's say it is find out mole fraction. Find out mole fraction of, simply it may be written as molal aqueous solution of, let's say, NaCl. Or you can revise the question. It is find out mole fraction of NaCl in its, molal aqueous solution. I hope now language is better. You have to find out the mole fraction of NaCl in its molal aqueous solution. So obviously, as per mole fraction of NaCl is concerned, it is moles of NaCl out of total number of moles. If you just try to imagine, let's say in a given vessel, if you just try to imagine, let's say in a given vessel, let's say इस पूरे vessel में if we have, let's say NaCl aqueous solution, the meaning of molal solution is its molality. Its molality is 1 mole per kg. Its molality is, let's say, 1 mole per kg as a molality of the solution is concerned. Molal solution. And given molal solution, if we have to find out mole fraction. So 1 kg means, you can imagine, let's say with 1000 gram of water, it has 1 mole of NaCl. So you need to just find out moles of water in 1000 gram. So the moles of water in this 1000 gram should be equal to, let's say, 1000 divided by 18 moles of water. And thus, as per mole fraction is concerned, mole fraction of NaCl is NaCl mole, which is 1, divided by total number of mole, which is 1, and it is 1000 divided by 18. Should be equal to 18 divided by 1018, comes out to be 1 divided by 56.56. As mole fraction of NaCl is concerned. So if we have to find out mole fraction of NaCl in its molar aqueous solution, its molality is 1 mole per kg. It is same as 1000 gram of water, and 1 mole of NaCl. With 1 mole of NaCl, we have 1000 divided by 18 moles of water. And finally, let's say mole fraction of NaCl is 1 divided by total number of moles, comes out to be 1 divided by 56.56. Next question. It's the question number 8. Find out molality of, it is, suppose 2 molar aqueous solution of, you have to find out, let's say, molarity of 2 molar aqueous solution of NaOH if density, if density of solution, if density of solution is 1.2 gram per milliliter. So find out molality of 2 molar aqueous solution of NaOH if density of solution is 1.2 gram per milliliter. You have to find out molality of 2 molar NaOH solution. So again, I'm repeating the question, the meaning of the question here. Let's suppose in a given vessel in which we have solute as well as solvent, As per solute is concerned, it is NaOH, and as per solvent is concerned, it is water here. So as per, let's say, solvent is concerned, here suppose you can imagine this may be total volume of this content, total volume of this solution. Total volume of solution, let's say you can just try to imagine, suppose if we have 1 liter of solution. Suppose if we have, let's say, 1 liter of solution. Out of this 1 liter of solution, we already have 2 moles of NaOH, as its molarity is given as, let's say, 2 molar. Density of the solution is given as 1.2 gram per milliliter. Density of solution is given as, let's say, 1.2 gram per milliliter. So eventually as per, let's say, question is concerned, its molarity is given, its density is given here. So out of 1 liter of solution, it consists, out of 1 liter of solution, it consists, 2 moles of NaOH. 2 moles of NaOH means 2 into 40, and it is 80 gram of NaOH. So for 1 liter of solution, it consists 2 moles of NaOH, which is nothing but 80 gram of NaOH. As density of the solution is given, which is 1.2 gram per milliliter. Total mass comes out to be, let's say, 1200 gram for 1 liter. So it is 1200 gram is the mass of solution. Out of this, 80 gram is the mass of solute only. So mass of solvent. Mass of solvent is total mass of solution minus of mass of solute, and it comes out to be, let's say, 1120 gram of solvent. Eventually, if we have to find out molality, small m should be equal to moles of solute versus 2 moles of NaOH given, mass of solvent, and you have to find out of 1000, out of 1 kg. So as per molality of solution is concerned, I hope you understand the fact that we can find out mass of solvent as per definition of molality is concerned. We require mass of solvent. It is out of 1 kg of solvent, moles of solute. So overall, it comes out to be 1.78. 1.786 molal. And a molal means, let's say, small m, moles per kg. So it's molarity, which is molecular mass. Molecular mass is given as capital M, which is molarity. It is given as 2 molar, and molality comes out to be 1.786. So whatever we have done in this question, we can figure out it separately also. For example, if molarity is given, so small m, which is molality, should be equal to capital M, which is molarity, moles of solute, and it is nothing but, let's say, 1000 multiplied by, let's say, rho, density of solution, minus, capital M, and it should be, let's say, molecular weight of solute. Smaller m should be equal to, let's say, capital M divided by 1000 multiplied by density of solution minus capital M multiplied by molecular weight of solute. So this is how you can find out the relation between molarity and molarity. So you just need to know how you can find out these type of relations, or without remembering these relations also, depending on the questions, depending which quantity is given and which quantity you have to find out, you can correlate also. So another question related to interconversion of molality and molarity is, let us suppose a mole fraction is given and you have to find out molality and molarity. So next question, let's say, find out molarity and molality. Find out molarity and molality of you have to find out molality and molarity of aqueous urea solution. Find out molarity and molality of aqueous urea solution in which mole fraction of urea is given as 0.2 and density of solution is 1.2 gram per milliliter. Now here mole fraction of urea is, let's say, given as 0.2 and density of solution is, let's say, 1.2 gram per milliliter. So as per answer is concerned, here as per solution is concerned, again in given solution we have urea as well as water as our solvent, and depending on moles, mole fraction of urea is given. So here first you can imagine, out of, let's say, total moles of solute as well as solvent, so total moles, you can imagine it is X as the total moles, and total moles may say, here first you can see, let's say, moles, you can find out moles as per moles of urea is concerned, which is solute, is 0.2x if X is total number of moles. Similarly, as per water is concerned, H2O, it is 0.8x. You can find out, let's say, mass of urea is 0.2x multiplied by 60 gram moles multiplied by molecular mass, and mass of water, it is 0.8x multiplied by 18 grams. It is the mass of water. Same as per, let's say, total mass is concerned, which is mass of solution. Mass of solution is, you can just add these two terms, comes out to be, I hope, 26.4. So 26.4 gram. As per total mass of solution is concerned, it is 26.4 gram as mass of solution. Here, as per volume of solution is concerned, volume of solution should be, let's say, 20. Oh, there has to be some x term there. So it is solution mass is 24.x gram. So volume of solution should be total mass of solution divided by density of solution, which comes out to be 1.2. I hope it comes out to be 22 x milliliter. So I'm repeating again, as per my question is concerned, here everything is given to you, including it is given as, let's say, mass of solute. Now you know the mass of solvent in terms of x, volume of the solution. So to calculate molality or molarity, whatever you need, now you have everything. You have to just apply their formula, related formula there. So as per molarity is concerned, it is moles of solute, which is 0.2x divided by volume of solution, which is 22x milliliter multiplied by 1000. And similarly, as per molality, the small m, it is 0.2x as the moles of solute divided by total mass of solvent only, which is, I hope, 14.4x, and it is multiplied by 1000. I'm repeating again, as per total mass of water is concerned, it is 18 8 it will be 144. I hope in the same term, 18 8 yeah. Yes, 18 8 144. So total mass comes out to be the same as this only, 144x. As per molarity of solution is concerned, it comes out to be 100 divided by 11. And as per, let's say, molality is concerned, it comes out to be 200 divided by 14.4. So overall, as per molarity and molality is concerned, it is 100 divided by 11, it is 9.09 approximately, this much molar. And as per molality is concerned, it is 200 divided by 14.4, comes out to be 13.89 molal. So here it is molarity, and it is small m as molality. Molarity and molality. I hope you note down this thing. So now it is time to revise whatever we have done today. As per concentration term is concerned, this concentration term will repeat again and again in complete chapters, different chapters of chemistry. Whenever we'll do, let's say, ionic equilibrium, chemical equilibrium, redox titration, volumetric titration, chemical kinetics is chapter in class 12, electrochemistry chapter in class 12. So as per all fundamentals of the chapter is concerned, they are actually related to the mole concept and stoichiometry only. So molarity means moles per liter, moles of solute per liter of solution. Molality is moles of solute out of 1 kilogram of solvent. Mole fraction is moles of solute out of total moles of solution. Total moles of solution means moles of solute as well as moles of solvent. And as per percentage is concerned, it is obviously out of 100. So if it is percentage weight by weight, it is mass of solute out of 100 gram of solution. As per percentage weight by volume is concerned, mass of solute out of 100 milliliter of solution. And similarly, percentage volume by volume means it is volume of solute in milliliter usually out of 100 milliliter of solution. So from the next lecture, we'll do, let's say, equivalent weight and, redox titration, or, balancing of redox reaction and redox titration, basically. So that's all for today's lecture.